In this lesson, we're going to be looking at a different type of sequence other than arithmetic. So let's take a look at an example first. If we have the sequence 2, 4, 8, 16, what number would come next? Well, we're starting with 2. We double it to get 4, double 4 to get 8, double 8 to get 16. Because we notice if we just did 2 plus 2 to get 4, if we add 2 to 4, we're not going to get 8, we're going to get 6. So that wouldn't fit the pattern of this sequence. So the next term would be 32. Next term after that, if we double 32, we would get 64. And if we double 64, we wind up with 128. So those are the next 3 terms of that sequence that we got by doubling. And this sequence is an example of a new type of sequence called a geometric sequence. And in a geometric sequence, each term is obtained by multiplying the previous term by some constant. So you're always multiplying by the same thing. In the case of the sequence we've just looked at, you're multiplying by 2. So here's an example to generate a geometric sequence. We'll start with 3, and then each term will be multiplied times 2 from the term before. So we have 3 times 2 gives us 6, 6 times 2 gives us 12, 12 times 2 gives us 24, 24 times 2 gives us 48, 48 times 2 gives us 96, and we could carry on as long as we wanted. So the constant that we multiply to generate a geometric sequence is called the common ratio. And with arithmetic sequences, if you recall, we find the common difference by subtracting 2 terms that come consecutively or right in a row. With a geometric sequence, we divide the 2 terms. So we take a term, that's our Tn, and we divide it by the term that comes before, that's our Tn minus 1, and that will give us the common ratio. And it doesn't matter, just like with the arithmetic sequences, which term you pick to find which 2 terms you pick, as long as they're right in a row. So now that we have multiple types of sequences we're looking at, arithmetic and geometric, we do need to be able to tell the 2 apart. So for these 3 sequences down here, we're going to identify if it's arithmetic or geometric to start off with. Sometimes it can be a little bit tricky to tell the difference, but generally what you want to know is if you're adding the same number over and over again, or if you're multiplying by the same number over and over again. So let's see. For the first one, if I say, I know that 8 plus 16 is 24, but if I add 16 to 24, I should get 40 and not 72. So that tells me that there isn't a common difference. So I'm going to look at multiplication. I can see that 8 times 3 equals 24, and 24 times 3 equals 72. 72 times 3 gives me 216. So I can clearly see that this is a geometric sequence. Okay? For number 1. That is my A. For B, we're asked to state the common difference or common ratio. So to find the common ratio, we're going to call it R, which differentiates it from the variable D that we used for difference. So R, I'm going to just pick 2 terms. So I'm going to pick the first 2 because they're small. It's 24 divided by 8, which equals 3. So a lot of you may be able to just determine it by looking. You know 8 times 3 is 24. You may know 24 times 3 is 72 as well. However, there may be geometric sequences where it's a little bit more difficult to find the common ratio just by looking at it. For example, if it involves fractions or decimals. So it is important to remember that we divide to find the common ratio. Okay, now we're going to find the next 2 terms. So our 5th term is going to be 216 times 3, which is 648. And our 6th term is going to be 648 times 3, which is 1944. And in case you're wondering, no, I did not do that in my head. I do have access to a calculator as well. So, next sequence. Well, this one looks like it's going down pretty fast. So you might think that it is a geometric sequence. But I noticed 108 and 72. 72 doesn't actually divide evenly into 108, so I'm going to try again arithmetic first. So 108 to 72, we're going down 36. 72 to 36, we're going down 36 again. 36 to 0, we're also going down 36 again. And the 0 is actually a clue that this is going to be an arithmetic sequence, even though the numbers are quite big, which is what you often get with geometric sequences. And we can't multiply our way to 0 without multiplying by 0. And since we have other non-zero terms, we know that this can't be a geometric sequence because there's no way we could multiply something to get 0 unless the common ratio were 0. So we know we have to find a D, not an R, and we've already located that by trying to determine whether it's arithmetic or geometric. Our common difference is negative 36. Again, going down, negative common difference. For C, we're going to continue under 0, so T5 is negative 36, and T6 is negative 72. All right. Last one, and we've got some fractions. So we go negative 3 to 2 is adding 5. If we were to add 5 to 2, we should get 7, not negative 4/3. This is a pretty good clue that we've got a geometric sequence on our hands. And now, since we are involving fractions, I'm going to divide. So I'm going to pick my first two terms. I'm going to do the R equals, I'm going to do just T2 divided by T1 because those are whole numbers and it makes it a little simpler than dividing fractions. So we get 2 over negative 3, which as we know is the same as negative 2/3. So we can have a negative number as a common ratio as well. And what will happen when you have a negative number as a common ratio, as you can see in this sequence, is that you will alternate between terms that are positive and terms that are negative. You will never have a geometric sequence that is all negative numbers because multiplying by, well, actually, I take that back. You could. If you have a geometric sequence that is all negative numbers, your common ratio will not be negative. If your common ratio is negative, you should be alternating back and forth. Okay. And for part C, we're going to do the next two terms. So we're going to multiply by negative 2/3. So my T5 is going to be negative 16 over 27. Important to keep the sign correct. And T6 is going to be 32 positive over 81 because we're multiplying by negative 2 over 3. So now we're going to see, we've got a little bit of, we can tell the two apart. Now we're going to see if there are some similar shortcuts we can use for geometric sequences, like the ones that we used for arithmetic, to find the general term of a geometric sequence. So we have a sequence 8, 12, 18, 27. So let's figure out what our common ratio is. 12, I'm going to do 12 divided by 8. Again, smallest numbers sometimes are the easiest. And I get 1.5. We're going to do 1.5 just to make it a little bit easier. So if we look at our sequence, we have 8, 12, 18, 25. I would have to multiply by 1.5 a whole lot of times to figure out what T100 is. And I don't really feel like doing that. Not at any time of day, not any day. Don't want to multiply by 1.5 that many times. So what I'm going to do is, just like I did with arithmetic sequences, I'm going to try to look for a pattern. So T1 is just T1. T2, I multiply by 1.5 one time. Okay? And here, I'm multiplying by 1.5 two times. For T4, I'm going to multiply my previous term by 1.5, so it's 8 times 1.5 times 1.5 times 1.5. And now that I'm writing this repeated multiplication, I remember I have a shortcut for repeated multiplication. So this is 8 times 1.5 to the power of 3. And I could actually similarly go back and write here, this is 8 times 1.5 to the power of 2, and this is 8 times 1.5 to the power of 1, although it's a little silly to write the 1. But the reason I'm doing that is so then I can go back and I can look at how the term number relates to my exponent. So I have 2, 1, 3, 2, 4, 3. So I notice the exponent of my common ratio is 1 less than my term number. And I'm always multiplying by that first term to start off with. So if I want to find T100, I'm going to do 8 times 1.5 to the power of 1 less than 100, so that's the power of 99. And now your calculator might not like this one, but this is approximately 2.168 times 10 to the power of 18. That's 10 with 18 zeros, and we are in the quintillions here. So geometric sequences can get big, especially if they have common ratios that are not between -1 and 1. They can get big really fast. So you just have to be aware that your numbers may come out larger for these kinds of problems. So now let's try to generalize it for any common ratio in any T1. So instead of 8, we'll replace 8 with T1. So we have 8 T1R. We have 8 T1. We have T1R squared. So this is going to be T1R to the third. And this one would be T1R to the power of 99 to find T100 for any geometric sequence. So the 100th term was multiplied 99 times by the common ratio. And let's see if I can fix that. Okay. So we want to know how many times the nth term would be multiplied by the common ratio. So the nth term would be multiplied by the common ratio n minus 1 times. Whatever the term number, 1 less. Just like with arithmetic sequences, except instead of adding, we're multiplying. So this is our formula for finding the nth term of a geometric sequence. T sub n is equal to T1, our first term, times the common ratio to the power of n minus 1. Now, there's one thing that gets a little picky about this where we have to think about order of operations. So we've got our general term, first term, common ratio, and position, just the same as arithmetic sequences. The only difference is we're using an R instead of a D. Okay, let's find the formula for the general term of the two sequences over here and then calculate T9. This is going to show us what some of the actual math difficulties you might run into with this formula. It's pretty straightforward, but there are a couple little tricks. So first thing we want to do, we've got our formula Tn equals T1 R to the n minus 1. So the first thing we want to do is find the general term, and for that we need to know what T1 is, and we need to know what R is. So T1 is relatively simple, it's just the first term, so that's 5. R is the common ratio, so I'm going to divide 15 over 5, which is just 3. Or you can just have a look at it, you may be able to figure it out. So my T sub n, all I'm going to do is replace the T1 with 5 and the R with 3. Notice that I am not writing this as 15 times to the power of n minus 1. And the reason is that even with algebra, when I have T1 times R to the n minus 1, order of operations applies. So you have to be well aware of your bedmass and that exponents come before multiplication. So you're going to do the 3 to the power of n minus 1 first and then multiply by 5. When you're calculating it, rather than leaving it up to your calculator, I highly recommend that you do 3 to the power, or whatever your common ratio is to whatever power you need to raise it to, and then multiply by your T1, because it keeps you from having that order of operations mistake, because this is definitely not the same as 15 to the n minus 1. With 15 to the n minus 1, you're multiplying 15 n minus 1 times. 5 times 3 to the n minus 1 means you multiply the 5 only once and the 3 n minus 1 times. So let's find T9. So T9 is 5 times 3 to the 8 to the 9 minus 1, so 3 to the power of 8. So what I do, you use my technique, we're going to do 5 times whatever 3 to the 8th is, which your calculator will tell you is 6561. And that's going to give us a final answer of 32,805. Okay, so we do have to be careful about order of operations there. Let's try another example. So we've got this lovely sequence here. We've got a negative and it's alternating, so we can see we have a negative common ratio. Got our formula, Tn equals T1 r to the n minus 1. T1 is our first term, that's equal to 1/3. Our common ratio, this time we're going to have to do negative 1/6 divided by 1/3. Notice I'm not dividing the bigger fraction by the smaller fraction, just in order. Second one divided by the first one. Negative 1/6 divided by 1/3 is negative 3/6, which is negative 1/2. Remember, flip and multiply your fractions. Apologies, you may have thought you've gotten to pre-calc 12. You could leave your fractions behind you, but sad to say your fractions will never go away. So our Tn is going to be our T1, which is 1/3, times our r, which is negative 1/2, and I'm going to put that in brackets to the power of n minus 1. Because we do need to have, otherwise the negative comes out in front of the 1/3. We don't want that because it's supposed to alternate depending on what power you're raising the negative 1/2 to. So if I want to find T9, that's 1/3 times negative 1/2 to the 9 minus 1, which is 8. Negative 1/2 to the 8 is going to come out as a positive 256. So this is 1/3 times positive 1/256. Which equals 1/768. Okay, example 2. We want to determine the number of terms in this sequence. We're going to have to actually use a new mathematical technique in order to be able to do this. So let's write down the information we have. We have T sub n equals 236,196. Okay, that's our last term, that's our T sub n. Our T1 is 4, and our common ratio is 12 divided by 4, which is 3. All right, so we're going to start with our formula. T sub n is T1 r to the n minus 1. Okay, so now we've got some numbers we can substitute. We have 236,196 equals 4 times 3 to the power of n minus 1. So we're going to divide by 4, and we get 59,049 equals 3 to the n minus 1. Now, what we need to do, so you know how like if you square something, you can take the square root. If you multiply something, you can divide it. We have inverse operations that we can use to undo something when we're doing algebra. Problem is, I don't yet know an inverse operation for raising something a power to a variable exponent. I do not have any sort of way to reverse that. So when I get to this stage, I say, well, when you're raising things to powers, there's sort of a finite number of whole number powers you can raise it to. So I use the time-honored tradition of guess and check. And when I was making the notes for this, I have to say, this is not a lie. I am not making this up, not trying to make it quicker. I actually guessed right on the first try. And I guessed 3 to the power of 10. And when I punched 3 to the power of 10 into my calculator, lo and behold, it was 59,049. No lie, I didn't try 3 to the 9th first, I just tried 3 to the 10th, so I don't have any lovely other guesses to show you. So what we wind up with is 3 to the 10th is 54,9. But we have to be careful because this is 3 to the n minus 1 is 59,049. So this means n minus 1 equals 10. Not n, but n minus 1, and n is equal to 11. Now that is our final answer. We answered the question. There are 11 terms in the sequence. Okay, If 28 is the second term of a geometric sequence and 1792 is the fifth term of the sequence, what is the first term of that sequence? This sounds like a systems of equations question, but here's the problem. Geometric sequences do not create linear equations. So we're going to have to create some equations and figure out how to solve a nonlinear system of equations. Okay, so let's take a look. If 28 is the second term of a geometric sequence, so that means T2 is 28, and 1792 is the fifth term, making T5 1792. We can write down a couple of different equations with these variables. So we get T2 equals T1 r to the power of 2 minus 1. So we get 28 equals T1 r. Okay. Now we have t to the power of 5 equals T1 times r to the power of 5 minus 1. And so replacing it with 1792, we get that is T1 times r to the fourth. So what I'm going to do now is I notice I have a T1 and an r. So this is equal to T1 times r times r times r times r. And this works for any number. So what I'm going to do is I am going to substitute T1 times r. We know that T1 times r equals 28. So I'm going to replace the T1 times r with 28. So I get that 1792 equals 28 times r to the power. We have 1, 2, 3 r's left over, so that's r to the power of 3. Now I can divide both sides by 28. I get 64 equals r to the power of 3. So that means that the third root of 64 is equal to r. So if I have a power, I can take that root to find what the number is. You do have to be careful though. We have r to the third, the cube root of 64 only has one solution. If it were the square root or the fourth root or the sixth root of 64, that would have more than one solution, because with even roots, there's always a positive and a negative solution. If you're trying to solve an equation, like 64 equals r to the fourth, there's always the positive square root and the negative square root. So just recall that even roots mean plus and minus answers. So there could be more than one possibility for what the common ratio is in this case. It could be here, because we have the second term and the fifth term, so we have an even term and an odd term, and they're both positive, we know we can't have a negative answer. So our common ratio is equal to just 4, and that's the only possibility. Okay, so that wasn't what the question was asking. It wanted the first term of the sequence, but since we know that 28 equals T1 times r, and we know that r is 4, so 28 equals 4 T1, we can easily find that T1 is equal to 7 by dividing. Put a box around that. Okay, last question. This may have some relevance to some of you if you happen to be a car owner. So we have a car's value depreciates by 20% each year. Today the car is worth $20,000. How much will it be worth in 4 years? So this is a little bit complicated. So when we're depreciating by a percentage, increasing or decreasing by a percentage creates a geometric sequence. We are decreasing by a percentage. So what we are doing is we are multiplying by 100% minus the percent that we've taken away. So if we're taking off 20% every year, that means at the end of each year, we have 80% of the car's value remaining. So our common ratio is 80. And if we want to turn that into a decimal, we will turn it into 0.8, which will be a bit easier to multiply. Now, we know that our T1 is 20,000. But what is our N? And this one is a little bit tricky to think about. So let's think about years. So if we're starting today After 1 year would be the second value. After 2 years would be the third value. After 3 years would be the fourth value. And after 4 years would be the fifth value, because we're talking about at the end of 4 years. At the end of 4 years, not at the beginning of the fourth year. Okay, so at the end of fourth years, we've started at our 0. We're actually starting at 0 years from today. That's our T1. So we're going to end up with our 4 years, end of 4 years being our T5. So in this case, n is equal to 5. And if you need to, you can kind of draw it out in your head. Think about starting 0, 1 full year, that's to 2, 3, 4. Okay. The other option, if you don't like that, is calculate the car's value after 1 year and make it T1. That's another possibility. Okay. So our T5 is what we're actually looking for. So I'm going to write my formula. T5 equals T1 times r to the n to the 5 minus 1. So it's r to the power of 4. So we have T5 equal to 20,000 times 0.8 to the power of 4. And I'm going to carefully do the 0.8 to the power of 4 first and then multiply it by 20,000. And I wind up with 8,192. Okay, and that's how much the car will be worth. The car will be worth $8,192.